Hello everyone, I'm Dominic Manno from Haswell National Laboratory. I lead our storage research team in the HPC division here at LANL. First, I'd like to thank the organizers for having me speak today. And today I'm going to walk through LANL's work in computational storage, our implementation, and our ongoing efforts. We've been sharing a lot of these details in various forums and even directly with some of the vendors likely in the audience. And in fact, I gave a similar talk to the SNIA Computational Storage Working Group. So apologies if some of this is repeat content for you, but with that being said, let's go ahead and dig in. As I mentioned, this is focused on our vision for computational storage and simulation science, but we do think there is some overlap with industry or cloud, especially as we move into the data analytics use cases. And one of our main goals is to use and contribute to the open source implementations, upstream any modifications we make, and really leverage the broader community, especially in these early exploration days. So we're going to start off with a very brief background of the current generation system. This system is called Trinity. So Trinity is made up of about 20,000 nodes. It was first deployed in around 2016. The nodes are a combination of Haswell and Knight's Landing. So in total, there's a few million cores, approximately 2 petabytes of DRAM, about a 4 petabyte NAND burst buffer. So this is an all-flash file system dedicated for the high performance tier. There's also about 100 petabyte in capacity scratch tier. This is disk-based file system, approximately a terabyte per second. And then we've got a large capacity tier, approximately 60 petabytes. That's called CAM page storage. That's a little bit of a slower tier, but designed for highly protected data that will live there for on the order of months to years. And then lastly, we've got a large tape archive, which is, again, quite a bit slower, but data that goes into the archive will live there forever. So as we move forward into the future, we expect systems to grow. Although as we move to more advanced capabilities like high bandwidth memory, we likely see an initial step down in memory footprint and likely flash capacity. I'll describe this a bit more later, but we probably also see our 2 fast tiers, the burst buffer and scratch file system depicted here. We likely see these two systems merge into one tier. And then in terms of the growth of our capacity tier, we expect the campaign storage tier to grow in capacity to something on the order of half an exabyte. Okay, so just a quick overview of the structure of today's talk. First, we're going to discuss our initial efforts in computational storage. I kind of describe these as data agnostic operations. Think storage system operations. And then we'll talk a bit about our first data analytics use case, and then close out with a more complex analytics use case and an example of a working prototype of a system. Our first case was developed to help us understand what it takes to deploy a highly efficient all-flash-based storage endpoint. We refer to this effort as the Accelerated Box of Flash, or ABOF for short. And this was a partnership between LANL, Adaptiv, Aon, NVIDIA, and SK Hynix. It's been in the works for quite some time. Okay, let's start with the current generation of HPC storage designs. The large cluster on the left representing something like Trinity, obviously built to support mission-critical applications. Like I mentioned a few minutes ago, a single job can consume the bulk of compute nodes. And so these things run for 6 or more months at a time for a single simulation. They checkpoint periodically to ensure forward progress in case of hardware failure on the compute node side. And so progress of the simulation is dependent on achieving the maximum performance from the I/O subsystem, because during the write phase, there's no computation going on. All computation is paused. And so as we move out towards the right, we see the burst buffer. These are dedicated nodes or dedicated servers with flash installed that sit on the same high-speed fabric as the compute nodes. So because of the small capacity, and it was initially the first trial of something like a burst buffer, we also deployed a high-performant disk tier. This is represented by the Lustre setup out on the far right. Because we wanted to provide a minimum of a terabyte per second of bandwidth in this tier, it led to quite a large capacity, much larger than we would normally deploy for a high-performance tier. It was likely the last disk-based tier we buy for a high-bandwidth use case. But the biggest thing you should take away from this diagram is that the design is really tightly coupling storage media and storage servers. So it's super rigid design, and it really prevents any augmentation while the system is in production. Now, if we start thinking about designing for the future, with flash prices dropping since Trinity and NVMe and NVMe ONF becoming more standardized and popularized, we realize we can accommodate various workload requirements, and we can do it mostly with the same hardware. So, but by doing so, now we can scale out file system services separately from the file system media based on use case. So we no longer have this rigid monolithic design that we were locked into before. And then each service can meet a workload need, and it can do it efficiently. So there are two alternatives to this, a hyper-converged architecture, which some sites can probably take advantage of based on their workloads and use cases. Or there's dedicated islands of storage for each use case, but this can become costly in multiple ways. So this design lends nicely to exposing storage devices directly to compute nodes, or even behind the storage servers, as I already mentioned. And then also, it doesn't really lock us into a single fabric enclosure. If there's a new fabric enclosure that we become interested in, we can easily integrate it into the system. Okay, so that's the background on how NVMe and Flash are impacting our designs. But this talk is supposed to be about computational storage, so let's dig into the computational storage details. So as it turns out, just pairing Flash with storage servers and our current HPC file system stacks doesn't turn out to achieve the levels of performance that the Flash devices are capable of. Actually, as we will see in a minute, it turns out that our RAID and compression techniques create the need for multiple passes over the data in memory. And as we've been hearing in multiple forums recently, memory bandwidth of servers just can't keep up with this. The networks and the drives are becoming too fast to need multiple passes over memory. And so this is true today. It likely won't always be true, so we want to keep that in mind as well. But as we began testing with all Flash file systems, we realized there was a limitation in performance. To make matters worse, we buy Flash to meet bandwidth requirements and lesser so IOPS, but those workloads are becoming more popular. So this generally means we don't have a ton of capacity in this tier, and any space savings we can get, we certainly want to take advantage of. But as I mentioned at the top of the talk, when you're simulating physics, the idea here is high entropy. So it's floating point values, and this stuff just doesn't compress all that well. So if you want to compress it, you really need something powerful like gzip. And running gzip on a CPU, as most of us have seen, is fairly slow, unless you have special accelerators. So here on the left, what you'll see is a plot using the test on an Intel Platinum dual socket, so a pretty high performing memory subsystem. And then the plot on the right is an AMD EPYC second generation. So also a fairly high performing memory subsystem, although maybe not quite the level as the Intel Platinum. So this is just running 1 megabyte sequential writes to a 10 disk NVMe drive setup. So the dashed line here is what we expect the raw block performance to be, and it's actually measured raw block performance there. And so each line, as it gets lighter, we're adding computational overhead. So that first dark line that's closest to the dashed line is just adding a small CPU calculation to calculate a checksum. That next line represents adding RAID Z1 overhead, adding RAID Z1, so one parity drive. So a little bit more of a calculation than a checksum. And then the final one is RAID Z2, which is adding two parity drives. And as we see, performance is degrading, but as we add a computation for RAID Z1 versus RAID Z2, it doesn't degrade anymore. So this was kind of one of our first light bulbs that said memory bandwidth might be a problem. So if we think about what our requirements are for designing an efficient usable storage endpoint, we certainly want to require parallel file system support. This is something that we deploy today and is needed for our checkpoint restart workload. So we certainly don't want to remove that requirement in our very first foray into computational storage. We expect millions of processes writing and reading to single parallel files and multiple files. So that is a use case that we want to enable. And for Lustre, we can use ZFS as an underlying component file system. There is another version, another file system based on EXT that can be deployed under Lustre. However, that doesn't provide data protection. So we chose the ZFS route. We certainly want to provide flexibility where we run what. And what do I mean by that? Things like erasure coding, compression, decompression, checksums. We want to make sure that we don't depend on a single piece of hardware that if it fails, our file system is down. We want to be able to run via the CPU, running ZFS, run it on a NIC that has accelerators, run it on an FPGA that has accelerators. So really don't tie ourselves down to a particular CSA, CSD, CSP approach, but kind of have the ability to use a mix of these approaches. And this is mostly to match changing performance economics and also data availability. We also want to attempt to follow emerging NVMe and SNIA computational storage standards. So we participate and help try to provide use cases that are interesting for that group. For example, NVMe peer-to-peer is something we're very interested in making sure we support. And then lastly, the solution needs to be broadly available. So ZFS is an open source file system. Lustre is an open source file system. It's a good marriage there. Okay, so what are some of the benefits we expect to see using a computational storage approach? So moving from something like LZ4 to gzip, we expect to see compression ratios increase from about 1.06 to 1 to about 1.3 to 1. So a pretty decent increase in compression ratios for scientific data sets. So that's important. We also expect to enable expensive coding and decoding to protect us against failures and more specifically correlated failures. We expect to have higher per server and per device bandwidths, given the memory limitation expectation we talked about a minute ago. Lower server costs and quantity. And then a kind of a nice side effect is that we also get to enable more than block as an interface. Okay, so here on the right depicts the accelerated box of flash. It's looks like a standard server with 24 NVMe drive bays in the front. But there's actually no CPU in this particular version of the ABOF. We have a variety of versions of the ABOF. Some of them have lightweight CPUs like ARM. Some of them have heavier weight like AMD. But in this case, we were exploring using an NVIDIA DPU, the blue-filled architecture, to test its capabilities as being the DPU of choice for the enclosure. We also have FPGA PCIe slots for FPGAs to be inserted. And then there's also the capability to install U.2 FPGA devices in the NVMe drive base. So in order to make the necessary changes for ZFS to benefit, we first needed a way for offload providers to provide their function definitions to a file system without embedding them directly. We don't want every provider to go to ZFS and have to write their own custom functions inside of ZFS. So this meant we needed a module that would allow providers to register their functions. This is using a standard API. And then to the file system uses to call the registered functions. This is called the DPU services module. It's open source. It's on GitHub. We're happy to take commits or bug fixes, anything like that. And then the second more important step was to modify the file system to take advantage of available offloads. So we wanted to be careful to make sure that all functions that were offloaded could also be completed using the CPU, like I mentioned before. That way, in case accelerators fail and when we still need to access the data. So the ZFS IO pipeline made this relatively simple. In the top here, we see the normal path the write would take through the ZFS IO pipeline. Each function likely requires at least one copy of the data, probably more. And you can kind of see how the ordering of the operation. So you take a copy from user space, you then do the compression operations, followed by the checksum operations, RAID Z, and then issuing IO out to the devices. If we look at the bottom half of the diagram, this depicts how we modified ZFS to enable computational storage. So each green box represents an offload capability on an accelerator. The ideal case is a pipeline fashion, so we can either leverage peer-to-peer or data that resides in the same accelerator with multiple functions. And then in the absolute worst case, you can pass data back to host memory for operations to be done there. So now if we want to start exploring some of those other workloads and provide a different storage service, we begin exploring data-aware offloads. And at Leno, we focused on two main types of simulation. First, particle simulation applications. This particle style simulation is a good fit for our first step into data-aware offloads. The data arrangement is relatively simple compared to our more complex mesh-based applications. So one of these important applications is the vector particle and cell code, or VPIC. And so VPIC is an MPI code. It scales to 100,000 processes. The mesh is fixed, so it's not changing over time. A record, if you will, consists of something on the order of 32 to 64 byte particles. This includes an ID, a cell ID, and then some features of the cell like energy, temperature, pressure, other things like that. So particles move freely between processes. There are probably millions of particles per node, potentially trillions of particles in the entire simulation. But the interesting phenomena about the PIC code is that interesting particles to a scientist at the end of the simulation is far, far, far fewer than the total amount of data written. So if we use our example of 10,000 or trillions of particles in the entire simulation, it could be that only 1,000 of them end up being interesting. So this is a huge data reduction problem, and it lends nicely to what computational storage can provide in terms of benefits. So when we look at the type of analysis done on VPIC applications, it does become clear that a few characteristics exist. The first one is a bit obvious, but the simulation or time step must complete before doing any analysis. So a full data set to look through for interesting data. Second, the scientists really are only interested in a tiny subset of data, like I mentioned. This is something like the highest energy particles, and it really turns out to be 1% or even less of the data. So this drives us to ask, how can we prevent the reading of petabytes of data when we're only interested in a tiny fraction? And so the way they do this data analysis today, they read the entire data set back into memory, and then they sort on the item of interest. So if they're interested in temperature, they will sort all of the records by temperature. If they're interested in pressure, they'll sort on pressure. But every time they're interested in a new field, this requires a new sort. So we're leveraging thousands of compute nodes, tens of thousands of compute nodes just to do sort operations, and probably multiple sort operations for interesting data. So this becomes extremely wasteful. And so there are some existing solutions that we can explore to solve this. But as I mentioned, the current application of sorting really doesn't solve the problem. So something like post-processing, I just mentioned this one. This causes excess data movement. This is the exact sorting problem. If we do in-transit processing, we either require a large amount of resources, compute nodes, CPU cycles, memory. And when you require that, the large jobs just become restricted, and they can't run as large as they want. In situ processing is valuable. This is sort of calculating a small amount of index within the application. But this is limited by only producing a small set of valuable indexes. So we began to explore indexing with CMU using a software approach. This work was called DeltaFS. Given the constraints I mentioned previously, we know we don't have many extra compute nodes available. And within a compute node, we don't have extra memory available. And this slide really doesn't do DeltaFS justice, so I'll link the papers, or you can easily search the papers. But effectively, the application thought it was writing and reading from one file for every particle in trillion particle simulation. But what it was actually doing was writing records to a massively parallel distributed sharded key value store that was sharded by particle ID. It achieves on the order of 8 billion particle operations per second. Yes, that is a billion. And if we by adding a little bit of time to index on the way out of the simulation into storage, we see roughly 1,000x gains in the analysis step. So obviously the indexing must scale, and it has to be efficient, but this leads to the epiphany that this is a perfect offloading opportunity. And quickly, just to reference the plots here. On the right there, we see the simulation growing in terms of number of particles, and obviously, if you're querying more particles, query time increases if you're only using the file-based approach. But DeltaFS stays fixed, and as you increase particles, the amount of time it takes to query stays relatively the same. And in the end, we see something like 5,000 times faster than the baseline. And then on the left there, you see the overhead added on to the I/O time as you add simulation processes. Okay, so we started this next step in work with SK Hynix, and initially it started with looking at the standard KV API that is published by SNIA. For scientific simulation, though, we really needed a few more operations and a little bit finer granularity of control. So this is really an effect of the specific workload that we're trying to offload. But we wrote up a rough extended API, if you will, that we thought would suffice, and we began working from there. So in this proof of concept, a fully ordered KV store was implemented in an accelerator that was connected directly to a ZNS SSD. The KV supports primary indexing, that's important for point queries, but also implements secondary indexing and histogram capabilities. So this leads to very efficient range queries, which are even more important to our scientific queries and are really inefficient to implement on something like a hash-based key value store. So our early results were very promising when comparing to a software implementation, in this case, LevelDB. You can see that on insertion, we were able to insert close to 18 times faster, and point queries were about 10 times faster. Since we published this data, we've since seen further improvements in both write and query phase. and these results will be published very soon. And we've also gotten a lot of interesting data by leveraging secondary index capabilities and the amounts of data reduction we see using secondary indexes. So finally, we'll close with the most complex use case, a data-aware offload for our complex applications. These applications are column-oriented rather than record. They're multidimensional, and queries will want to be able to query through the dimensionality, and they're a bit more complex to shard. So many continuum-oriented simulations are multidimensional in space, 1, 2, 3 dimensions, multidimensional in time. So this is across multiple time steps. And often a query of the data produced by these applications can have 2 to 5 more dimensions of variables. Think temperature, pressure, energy, momentum, materials, state, other things like this, that one might want to do a complex query over. So some example queries are things like tracking a shock wave through a material, or tracking the formation of an eddy, which is probably not so simple. But when single time steps are petabytes distributed across thousands of cores and address spaces, you can kind of see this complexity grows very quickly. So often applications use squares or cubes, likely polyhedrals, to represent a cell in which a single value of all the state array lives. Apps often use something we call AMR, adaptive mesh refinement, to be able to run through a larger problem than will actually fit physically in memory of the system. And they want to run this at full resolution. So through the simulation, the resolution is changed. They kind of drill into interesting parts of the simulation and kind of zoom out of the uninteresting parts from in different time periods throughout the simulation when something more interesting starts happening. And this can happen every few, or in the most complex case, every single time step. So talking about Lagrangian and Eulerian methods, these are used depending on whether it's better for the simulation to deform its mesh or not. So you can see in the upper right-hand corner of the diagram, each one of those pictures is basically representing a time step, and you can see that mesh or material deforming. So that's an example of a mesh that's deforming. So time steps are implicit in the storage system. What that means is that each time step or some number of time steps are written to storage as complete independent data sets. So because these simulations are often large, the space is decomposed somehow across these polyhedral cells, and groups of these 2-dimensional or 3-dimensional cells of the grid are decomposed onto different processes, different cores, different machines to enable parallel computation. So somewhere on the order of 10 to 100 state array variables exist in every single polyhedral. And the simulation processes do the computation on that process's cells, obviously, every single time step. But then after a time step, boundary information about these state variables is exchanged with neighbors. And then the mesh will be rebalanced based on the interesting properties of the simulation. And that reorganizes the state and data based on refinements that are required for the mesh. So in order to manage data in memory and read and write data from storage, these applications serialize the state data written out to represent a time step. The serialization is often such that each of the 10 to 100 variables is essentially a serial distributed array. And then this is distributed across all of the processes in the simulation. And the application has to store some kind of compact map, which describes how the serialized data is laid out across the 1, 2, 3-dimensional space across all the processes. So what apps will often use is the concept of Hilbert space curve filling to lay out this serial view of a 2 or 3-dimensional space. So the diagram on the top shows time steps in a simulation and how the cells might be distributed across processes and machines. In the lower picture, it shows a series of boxes with the cells in each box depicting in really 2-dimensional space, and probably super simplified here, but how each process or machine and its cells serialize the 1-dimensional space, serialize to a 1-dimensional space. So the lower picture also depicts how there's an overall serial map of the state across all participating processes and nodes in the simulation. So every single time step, there will be data that is serialized out of the participating nodes and written to storage. And this is written out in most of these applications case to a single large parallel file that the file system breaks up into multiple pieces. So the concept of changing the way applications write out their data logically or through a mapping function is to write out something like Parquet. They're already using something similar to a column-oriented format. It's just a binary format that custom binary format that they use. But if we want to move to leveraging data analytics tools, something like Parquet provides more power. And so we'll break up the single large file into many nice size chunks or files or objects to complete the Parquet row groups. And so as you can see, each variable ends up being its own column. And for each column, there is a simple min-max index for that row group. And there might be a footer, or there's likely a footer for the entire row group describing min and max for all the variables within a file. And then we can also explore the use of page indexes if we expect high selectivity for a particular query. Okay, so once we have the data written out in some columnar, likely Parquet form, with some extra information regarding where the files and objects and how they map to the global Hilbert space we discussed before. We probably also want to calculate some percentile information that Parquet doesn't currently support. That way it helps the scientists build more useful queries. So then we really need to reduce the data as much as possible, then likely build some multidimensional indexes, since like I mentioned, we expect queries to be multidimensional. Something like KD trees seem interesting to us to accommodate what the queries, the expected queries. So we do expect the KD tree approach to probably be expensive to build, and we're currently exploring the trade-offs and also looking at turning results from a columnar query into a record formatted store, so we get some order on the reduced data set. We're also extremely interested in calculating statistics beyond the min-max indexes, like I mentioned, so something more akin to a data distribution or percentile calculations, and figuring out how we could integrate that into either Parquet or just our storage system in general. So lastly, we wanted to think about this work in the context of our capacity tier. So could similar approaches I've discussed enable analytics in our highly erasure coded capacity disk tier? So we work closely with Seagate, and we've demonstrated this in a prototype using their HDD connected to an Envoy card. And so this allowed us to write Parquet files through the normal ZFS layer, but then provide an analytic interface that bypasses the file system and runs queries on the device using a file to LBA mapping. And so we call this mapping, we use libzdb to do the mapping from ZFS file names to LBAs. So we can see here that there's an explicit analytics path for running queries and an explicit data path that just flows through the normal ZFS pipeline. There are some alignment issues you have to think about when you're writing the Parquet out, because you want full row groups to fit onto a single hard drive. But this is really non-practical for a production deployment due to the layer violations that we've introduced here. But it definitely helped prove to us that this was an interesting path for disks as well. So we're certainly engaging further with Seagate on this work. And then so I'll close with our desire to collaborate in this space. We certainly hope to leverage the open ecosystem of data analytics formats and tools. We also think we likely need to move to something like a high performance object store to help prevent layer violations, as we've discussed in the Seagate collaboration. But we're still in the early days of this use case, and we're happy to have folks reach out to us for collaboration. And with that, I will close and take questions.